So now we have defined the computational block, computation of the causal attention. We will use that as the core computational step to form a practically useful attention block. So let's start directly from how the block processes the data, okay, and explain the mechanisms definition when we encounter them. So given the input of some data to the attention block, instead of directly send this data into the attention block, it applies an operation called layer normalization, which is just a scaling and a shift of the data so that the data can have some manipulated distribution, overall distribution. That is to prevent the processing to move the data distribution from, for example, here to here without adding any more information. But that is mostly heuristic, and if you have more interest in this kind of operation, you can read this paper for layer normalization. And I think there are some good blocks to discuss those techniques anyway. So I will not refer to other blocks in this discussion, but you know that when you read a paper, it is always a good idea to search the paper's name and see whether there are more intuitive blocks and how people compare that paper to other papers. Okay, so and the next, after this kind of transformation, the layer just send the rescaled and reshifted version of the input to the attention block and apply a residual structure, which of course I need to slightly correct my discussion here. I think here we have said the residual is within this attention block, but in my implementation, this block output here, okay, and we put the residual in the block construction, but computationally they are equivalent to each other. So basically there is nothing essential to correct. Okay, this is layer normalization. This is X here, and this attention block, well, it will then get into just a element wise addition to each other. Okay, so what's next? It will then do another layer normalization. Okay, before it sent the layer normalized input to a multi-layer perception block, which is just a very straightforward, densely connected neural network. The neural network contains essentially two blocks of multilinear perception, just the transformation, and which is separate split by a nonlinear transformation. And the nonlinear transformation, well, just another useful way of transforming the data people discovered in previous years' research, and the paper is here. So basically, this is the paper. So instead of doing the sigmoid function, you do the positive only function. But the positive only function, here you have non-derivable part, which is continuous but not derivable here. So people would like to use smooth function so that the gradient can propagate nicely. And in this function, instead of using the smooth function go into the realm of negative, it formed a nice shape in this way. Okay, if you are interested in this kind of discussion, you can read this paper. It's called Gaussian error linear units. So along the way, we expand the number of features by a factor. I think k has the default value of 4. So basically, here we are doing another layer of layer normalization, and then we expand that, and we do some nonlinearity using Gaussian error linear unit, and we then put everything back into the original dimension of the feature vectors. So that completes the computation of RL. Again, we have another residual link. So this will do the element-wise addition again. So this completes the computation of attention block.